So we continue our discussion on crystal systems and crystal lattices. Lastly, in my class, what we have referred to is that by now we have seen that these three are the most important crystal structures in a cubic system. So we talked about a cubic crystal system, in which we said that you can have either simple cubic or cubic I, also referred to as body-centered cubic, or you can have cubic F, or also called as face-centered cubic. And we have seen that what is the detailed description about FCC, how do you create that through a stacking sequence of A, B, C, and we have seen it in detail. We have also seen that what happens in the case of transformation of iron at around 910 degrees centigrade from BCC to FCC, which we say is a isomorphous transformation. In that case, we have seen that this transformation gives rise to the reduction in volume, which we said is nothing but also responsible for what we call as the increase in density of pure iron. Now, further, we have seen already that in the case of the basics of what we refer to as coordination number, in the case of a simple cubic one, this happens to be 6, that is 4 in its own plane and 1 above and 1 below. We have a coordination number of 8 for BCC and for a coordination number of 12 for your FCC crystal structure. Let's move forward. We have talked about FCC crystal structure. We have seen that this happens to be what we call as the conventional unit cell. The conventional unit cell for FCC or a CCP, also known as the cubic closed packed structure. This is the conventional unit cell, but a look at this also tells me that this unit cell does not happen to be a primitive unit cell. This is not a primitive unit cell. We recall the definition of the primitive unit cell was that a primitive unit cell was defined as the smallest unit cell. We also defined the primitive unit cell as that one which contains lattice points only at corners, or another definition of that was that a primitive unit cell is that unit cell which contains one complete lattice point. When I look at this unit cell, which we say is the conventional unit cell for FCC structure, we find that this is a non-primitive unit cell. Means it contains lattice points not only at the corners but at the faces also. So it has lattice points at the face diagonals also. So we say it is a non-primitive unit cell. And then let us see, the question arises that what is the primitive unit cell for an FCC system? If you now look at this figure carefully, we will see that what happens to be the primitive unit cell. And what I now show you here is actually the primitive unit cell of your FCC system. So this happens to be your primitive unit cell, in which we see here that the primitive unit cell here happens to be this one, where we have the corner atom, the face center, the face center from here, the face center from here, and then going to the face center at the top, the face center here, the face center here, and when you combine this together, we get that this happens to be the primitive unit cell for an FCC system, FCC crystal structure or a CCP crystal structure, which, if you look at it carefully, it has corner atoms only two, so it's only one, and the second corner atom is here. Rest of all are the face-centered atoms. So this happens to be your primitive unit cell here. We can sketch it very easily, and we shall be able to give it some numbers also if you are interested in that. Actually, lattice systems are, or understanding or studying crystal lattices is itself a subject, and that is why you find that this discussion is getting somewhat unending, that we are now not able to conclude this discussion, because there are so many things to be talked about in the case of lattice systems, that we continue doing that. But I am only touching upon the important ones, and let us see that what else is there in store today. So we find here that this happens to be your primitive unit cell, or if I sketch it properly, we say this is the primitive unit cell. So this description is for the primitive unit cell. This is a primitive unit cell for a FCC structure, and if you sketch it in 3 dimensions, this is what you get. So in a way, I can say here that this primitive unit cell for a cubic system happens to be represented here with this descriptor here, and stacking of this in 3 dimensions space will actually give you a FCC crystal structure. Okay, let's move forward. I come back to this table where from which started our discussion. We say this table describes the 7 crystal systems along with their variants. So in these 7 crystal systems, we find that you can have primitive, you can have body-centered, face-centered, and end-centered. And out of these, you can say 7 crystal systems, we create 14 Bravia lattices. These are 7, 3, 2, and 2. We will answer today that why you find certain things which are missing here, like just the point here that why we find that this end-centered cubic is missing here. I will answer it today. We have already said that there are vacancies here in this table here. Although you could have 7 into 4, 28 possible Bravia lattices, but we have only 14. So we find that some of those absentees here are actually maybe duplicates. So we will see today that what happens in the case of this structure, which we say is end-centered cubic. End-centered cubic. Why we find that it is absent here? So let's move forward. So we find here that if you talk about an end-centered cubic system, this is how it will look like, the end-centered cubic structure. So in a cubic crystal system, what we see here is that you can have a possibility where these two opposite faces of the cube are having the lattice points. So these are the blue ones are the additional lattice points in addition to those which are at the corners. So we find that these are at the corners here, and we have these two which are at two opposite faces. So this may constitute what we call as a cubic eye crystal structure. But we find that it is missing in the case of Bravia lattices. It is not present there. One reasoning for that we will explain just now is that, okay, if you now look at this descriptor here, we find that you have the end-centered cubic lattice shown here. But if you just see that, let us say we are trying to now go for a 3D imaging, where we find that there are, let's say, 4 of these unit cells which have the lattice points at their opposite faces also, And if you now see it carefully, we may find that this happens to be your end-centered cubic lattice again. But why it is absent, we will see just now. Okay, why it is absent, let us look at it. So we find here that these are, let us say, the two ones. And when I look at the two unit cells, which we say are this one and both of these unit cells, they represent a cubic eye system, that is end-centered cubic lattice. But when you look at this carefully, we find that these lattice points which are at the face here, the blue ones, along with those at the corners, they themselves create a unit cell. So they themselves create a unit cell. So this is a unit cell in itself, which are the one which is shown here with these dotted lines. So this is a unit cell in itself. So this unit cell, if you look at it carefully, it represents a crystal structure which is already listed under the 14 Bravia lattices. And which one is that? Can you recall that? I hope it is very easy to remember. If you look at from the top of the table, you had cubic and then you had tetragonal. The difference here was that in the case of cubic, A equal to B equal to C, whereas in the case of tetragonal, you had A equal to B not equal to C. And we find here that you can find out the edge length, this edge length as well as this edge length. Both of them can be found here. And we will say that if the lattice parameter happens to be A here, lattice parameter happens to be A here, the face diagonal will be root 2A, and these two edge lengths here of this unit cell will be root 2A by 2. So we find here that if I write this as A dash, B dash and C dash, so this is A dash, this is B dash and this is C dash, and this is A, which we have already given. So you understand A dash is root 2A upon 2, which is nothing but A by root 2. And similarly, B dash also happens to be root 2A upon 2 or A by root 2. So I can say here that in this, the red unit cell which we have seen here, that A dash equal to B dash equal to A upon root 2. And clearly we can see what is C dash. C dash here happens to be equal to A because it is actually out of the original cubic unit cell. So C dash happens to be A. So this gives me that this happens to be an alpha, beta, gamma are all 90 degrees, and this gives me that this red unit cell which is contained within this, what we say we were assuming to be cubic eye crystal structure, it can be represented by a tetragonal P unit cell, primitive tetragonal. So this can be represented by a primitive tetragonal unit cell. This is the unit cell which we say is available to us. So this is your primitive tetragonal unit cell. The one which you see here, where this is A dash, this is B dash, and this is C dash. And we understand that A dash equal to B dash, and it has lattice points only at the corners. So that is why it is represented by these corner lattice points here. Now here, 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 and here. And it can be represented by tetragonal P. So tetragonal P is already there and that is the basic reason why we say that end center cubic has been removed. So, and this tetragonal P unit cell is also having a smaller unit cell volume. So once the basic understanding now is that because cubic I can be represented by a tetragonal P unit cell, that is why cubic I is absent in your 14 Bravia lattices, because we find we said 14 Bravia lattices means these are the unique ways in which lattice points can be arranged in a three-dimensional space. And because this one cubic I does not happen to be a unique way, because it can already be described by another system which was tetragonal P, and that is why we remove that, and it is not available to us in the 14 Bravia lattices there. So cubic C has been removed. What about face-centered cubic lattice, which is actually available to us? So if you remember, we are saying that face-centered cubic or CCP is one of the lattices which is a very common one and a very important one. So let us look at that. So if you take this FCC conventional unit cell, and if I add one more unit cell here just for ease of understanding, and we try to create a smaller unit cell in it, we find that it looks similar to what you have seen in the case of your previous slide where you said it was tetragonal P. Now we find that this length is, let us say, A dash, this length is B dash. It is clear that A dash is equal to B dash is equal to root 2A by 2, where this happens to be your lattice constant A. And this C dash will be equal to A. So it gives me that this also is nothing but a tetragonal crystal system. A tetragonal crystal system where we have the lattice points at the corners, as well as, if you look at it carefully, you have one more lattice point here at the center of this unit cell. So you have the unit cell described here, which we are saying is representing your tetragonal I now. So we understand that this is another unit cell which is available to us. So it has endpoints, it has lattice points at the corners, such that now A dash is equal to B dash, not equal to C dash, alpha beta gamma is equal to 90 degree, and in addition it had one here at the center, this one. So this is another unit cell which we say is tetragonal I. So tetragonal I is also there, but going back to your 14 lattices, we find we have FCC system also retained there. So we now say that, okay, in our last example we said that we replaced your end-centered cubic. We didn't use that because we already had tetragonal P. But by the same logic, somebody can say now that you have tetragonal I, but still you keep on using FCC or bodies or face-centered cubic lattice. So it's there's a contradiction here. So we have a contradiction here from my last slide, where we find that in this particular case you are retaining FCC is retained, as well as you find that tetragonal I is also there. So if you go back to your table there, you will find that you are retaining both of them here. So you are retaining the cubic F as well as tetragonal I, whereas what you just described here, that a cubic F system can be also represented by a tetragonal I system, but we still retain that. So there is a contradiction here, which is not a contradiction once we go to one more discussion on lattice systems, that is known as symmetry. So we will see, if we have time, I will post more videos about symmetry. That actually the understanding happens to be that the lattices cannot be described just by the shape of the unit cell and the size of the unit cell. A better way and a correct way of representing crystal structures and lattices happens to be what we refer to as symmetry. But for a undergraduate course, this much discussion what we had till now, I hope is quite sufficient for us to move forward to next topics on what we will talk about as the Miller indices, and specifically Miller indices of directions and Miller indices of planes. So, thank you.